AVL tree, a self-balancing binary search tree or BST data structure that ensures efficient storage and retrieval of data.
In this video, we will take a look at inserting elements into AVL3. So let's take as an example. So let's say that we need to insert the elements 9, 15, and 20 in that order. Now, with every element we insert, we must remember to follow two steps. The first step is we need to insert the element as we would in a normal binary search tree. The second step is that we need to have to check whether any imbalance that occurred due to the node that just has been added. If the imbalance has occurred, then we must perform rotation. Keeping this in mind, let's look at how we are going to insert the elements. So let's start with 9. Currently, the AVL tree is empty, so I'm going to make 9 as my root. This is the element that we had added so far. Let's extend it to the external nodes. I'm indicating external nodes as a shaded node. Now that we have inserted 9 as we would to a normal binary search tree. So let's look at what the height difference is. So the external node are going to have the height of 0. 9 is going to have a height of 1, which is 1 plus the max of the height of each children, which 0. 1 plus 0 is 0. The height of 9 is 1. There's no imbalance at this stage. Let's go to the next element. Now, to this AVL tree, we must insert 15. So the first step is to insert 15 into this tree as though it removed a binary search tree. 15 is going to be greater than 9. So it's going to come to the right of 9. So let's see what the tree looks like once we add 15. So now we have added 15. I'm going to extend this node 15 with two external nodes. So this is how I would have added 15 if it was a normal binary search tree. Now I'm going to check the height differences. So I have a node added 15, so I'm going to start from its external node. External node have a height of 0. 15 will a height of 1. Then we check 15 sibling. The 15, the external node with the height of 0. The height difference is only 1, so that's acceptable. Then we go to 9. 9 will a height of 1 plus the max of 0 and 1, which 1. So 1 plus 1 is 2. So the height of 1 will be 2. Stage we're not finding any imbalances, so we are insert the next element. With that in mind, let's add node 20. So we add 20, so we go to 9. 20 is greater than 9, so it will be added to the right of 9. 20 is greater than 15, so 20 will be added to the right of 15. I've added 20, so now we're going to extend 20 with external nodes. Let's look at the height differences. So I'm going to start checking its height external node. External node, we're going to have a height of 0. 20, we're going to have a height of 1. And its siblings, we're going to have a height of 0. 9 is going to be there because 9 is less than 15. And 20 is going to be there because 20 is greater than 15. This is the final AVL3 insertion.
Here are the example of AVL3 searching. Let's search for key 6. First, start at root 10. Compare 6 with 10. Next, move left. Since 6 less than 10, traverse to the left, sub 3 rooted at 4. Then, compare with 4. Since 6 greater than 4, move right to the sub 3 rooted at 6. Key found. Key 6 is found. Return the node. That's all.
Hey everyone, good morning. My name is Mr. Dan Jeruka. Today we're going to tackle a super important and surprising fun concept in the computer science that what we call binary tree deletion. Now I know the deletion might sound a little crazy, but trust me, it's actually simple once you break it down. I'm going to show you to deleting the nodes from the binary tree work, and by the end of this video, you'll feel like a pro. Let's go! All of the deleting node with a one child. We have some to add. 10, we have to get to 5 in the 20, and that we call have a one child. Now we all know that he has one child, right? So let's delete it. The 20 has gone, so this is the result. 10, 5, and the last, the right, 30. Boom! We see right?
So we have a right rotation, and we have a set of 10, 7, and 3. Rotate the 7 into 10's position, then select a pivot, which is 7. Then select the 7's left child, which is 3, then right child, which is 10. And that is the final answer. In left rotation, we have the set of 3, 7, and 10. Rotate the 7 into 3 position, then select the pivot, which is 7. Then select the pivot left child, which is 3, then the right child, which is 10. And that is the final answer. In left-right rotation, we have a set of 3, 10, and 7. So copy the 3, then rotate the 7 into 10 position, and rotate the 10 into 7 position. Then select a pivot, which is 7, and select a pivot left child, which is 10, and the right child, which is 3. In right-left rotation, rotate the 3 into 7 position, and rotate the 7 into 3 position. Then write the 10 into the right rotation, 10, 7, and 3. Then rotate the 7 to 10 position, and select a pivot, which is 7. Then select the 7's left child, which is 10, and the right child, which is 3. And that is the final answer.
Balancing process. Left rotation, rotate the subtree rooted at node 5 to the right. Update balance factors, recalculate balance factors for nodes 5 and 10. This is the balance tree after balancing. This is the step-by-step by balancing. Identify the unbalanced node 5, determine the rotation, direction, right rotation, rotate the subtree, update balance factor.